look at a couple of limits, and we're going to look at this graphically a little bit, so you want to get your calculator out. Then I'm going to kind of talk through a more formal derivation of these two things. Okay, so what I'm going to try to show you is why this limit is equal to 1 and why this limit's equal to 0. Graphically is very easy to understand. So let's start that way. So I'm going to pull up my calculator here if I can find it. Let's just do the basic calculator here. So what I want you to do is just go to y equals. You do need to make sure that you're in radian mode. Okay, we haven't done much trig here so far, so press your mode button, get the radian highlighted, and be sure that you're in radian mode because you want to get the same graph that I'm going to get. Okay, so what we're going to do is in y1, I want you to put this in like this. Just put sine x, be sure you close parentheses, then divide by x. And we're going to graph that, and we're going to graph it on the window negative pi to pi. So what you want to do on that is once you get that put in your window, do it like this, put in negative pi, like that, and then it'll crunch it out for you. Then put in pi. Okay, we don't need to scale it by anything. It doesn't really matter. Let's take that pi, maybe pi over 2, but it doesn't really matter for what I'm going to show you anyway. And then for the y values, let's go negative 2 to 2. I'm going to start that way, and then that way you should be able to see what I want you to see on the graph. Now, from a mathematician standpoint, graphing doesn't prove anything. It only demonstrates what this limit probably is equal to. Only the formal mathematical definitions is going to be to prove this. So now what you want to do is graph it. And I did something wrong. Let's see what I did wrong. Yes, y minimum. I put the wrong thing in there. Okay, so let me get that fixed. Okay, y minimum I want negative 2. Y max I want positive 2, and then y scale you can say 1, okay, like that. So you can put that in. Now you can go ahead and graph this, and you can see kind of what you see. And we're going to just look basically at what the left and right hand limit is, just based on our technology, and kind of get the idea, okay? So you should end up kind of getting something like that, okay? And you can go a little further out on that if you want to. So the thing on this is let's trace it a couple of values. If we were going to do a left-hand limit as x approaches 0, you know, you can pretty well tell what it is, but let's kind of do like we did back at the beginning of the semester. If you put in like negative 0.01, what does it look like it's going to? Probably 1, okay? I'll do it one more time. If you went a little bit closer, like negative, you can put a couple of more zeros in there. You can pretty well tell that the y value is going to get closer and closer and closer to 1, right? The right-hand limit's going to do the same thing. If you did trace 0.001, you're barely to the right of 0, so you can see basically that that limit's going to go to 1. Are you convinced enough? Okay, now that's not a mathematical idea. I mean, it's not a proof or anything, but it's a demonstration at least that those limits are going to end up being 1. Now, all I want you guys to write on your graph, I do want you to go ahead and just put this on here, is put pi here, put negative pi here, put 1 there, and just draw a really rough graph just so that you kind of remember how that graph goes. So it kind of does something kind of like that. That's pretty bad, but you get the idea, okay? All right, so that's how that limit goes. Now, the next thing I'd like you to do is put this in your calculator. And again, I'll get my calculator pulled up here so you can see how I put this in. And I'm going to erase this. And now what I have to put this in like this now. You want to put in cosine of x minus 1 and then close parentheses and then divide by x. Now, one thing that you want to see on this problem is that you're going to have a 0 over 0 limit right here. Now, I'm going to take the calculator off just for a minute, but then I'll put it back up here. But if you plugged in 0, and I do want you to write this down, if you did the cosine of 0 minus 1 over 0, how do you figure out what the cosine of 0 is without a calculator? You go to the unit circle. Can't forget the unit circle. When you're at 0 radians, you have the 0.10. So what's the cosine? 1. It's the x value. Good. So you have 1 minus 1 over 0. So you have this 0 over 0 limit. Okay, so you basically have got some sort of a hole in the graph. The same thing basically on the last problem happened as well. I didn't write that on there, but you would end up basically have a little bubble in the graph like that. So you are discontinuous at x equals 0, but the limit does exist. Okay, so now if I pull up my graph and put this in, and just use the same scale on this, and if you type graph, let's see kind of what this graph looks like this. Okay. Now remember, what we're doing on this one is we're looking at the limit as x goes to 0 again. So again, if you just kind of observe this, if you went a little bit to the left of 0, it looks like it's going to 0, right? If I go negative 0.00 and put more zeros in it, the idea is it's just getting closer to 0. That 5e negative 5 just means 5 times 10 to the negative 5th power. It just means it's getting closer to 0. So if you look at that graph, it looks like the limit is equal to 0 when you do that, okay?
Right, when you entered into your calculator for the y value, did you just do cosine of x over x or cosine of x minus 1?
Like this, okay? Because we're looking at cosine x minus 1 all over x, and then you've got to have that numerator in parentheses or it won't evaluate that correctly. Okay, now just make a little sketch of your graph on this now. And just make it real rough. All I want to kind of get is just you guys get the idea just for your record. So we basically had negative pi, we had pi, and it kind of went and did something kind of like this. Okay, the idea was you have a bubble there, you have a discontinuity at x equals 0, but the limit does exist. Okay, the reason I'm going over these two limits is because mathematicians had to figure these two things out. Not this way. Of course, they didn't have a graphing calculator in Newton's time, but he did have the ability to go through and investigate it this way by hand, which is a little rough. But basically, mathematicians did a more formal proof of that. Okay, so let's go to the next page. And I'm going to just kind of talk through this. I don't expect you to really know this, but I like to show you kind of what the book did, and I'm just going to talk through this idea a little bit, because the main idea in a Calc 1 class is you want to get the idea of the derivatives of the 6 trig functions. So I want you to just kind of look at this. You're not going to really need to write anything on here, but this is a setup, and this is how mathematicians ultimately proved what the derivative of the sine is. Okay, they had to know something on here. So the idea with this is we got kind of this setup right here. And if you look at the area, there's actually 3 areas. If you look at this area right here, OAD is a triangle. OAD is this triangle right here. Okay, that's a triangle. Then we have a sector. From trigonometry, you guys remember what a sector is. It's just a slice of the circle, right? It's like a piece of pizza. Okay, the sector is here. So isn't the area of that sector bigger than the area of that triangle? Okay. And then you have the big triangle, which is OBC. So you're setting up an inequality. This area here is less than the area of the sector, is less the area of the big triangle. Does that make sense? What I'm talking about. Okay, that's an inequality. It's a valid inequality. Now, if we formalize this a little bit, there's a few things that I do want you to write down on here. So remember the area of a triangle. What's the formula for an area of a triangle? 1/2 base times height. Okay, so if you were doing the area of this triangle, I'll try to kind of highlight these, and that'll kind of help you see what I'm looking at these as I look at them. If you were doing the area of that triangle right there, first of all, the base would be OD, right? The height would be AD, so it would be 1/2 OD times AD. Okay, and that's what that is right there. Okay, now OD. Why in the world did they say OD is just equal to the cosine of x? This is a unit circle, by the way. Okay, so isn't the x value of a unit circle the cosine? Okay, so see what you have is this point A right here really is the cosine x, sine x, because we're in a unit circle. And then AD, isn't that the y value? So isn't it just the sine of x? Okay. So what I'm trying to show you is the idea that that right there technically is what the area of OAD is. Okay, if you look at it analytically and use this formula for triangle and the fact that that's cosine and that's sine, that's what you're going to get. Okay? Now, let me see if you guys remember anything about this from trigonometry. Do you guys remember what the formula for area of a sector is? That's easy to forget. 1/2 alpha r squared. Okay? So what you're going to do when you do the area of this sector, and I'm going to kind of erase a couple of things on here, because all I'm trying to do is just get you guys a little bit of an idea of how proofs work at this level of a class. So the sector would be this part right here. So now we're looking at that area right there. So if you kind of look at what has been put together, what you have here is you would have 1/2, okay, times the angle alpha is just x. Okay, I'm using x as my variable for the angle alpha. Then the radius is a unit circle, so that radius is 1, so it's 1 squared. So what you end up getting on this is just 1/2 x times 1, so you end up getting this right here. So the area of the sector can be given by x over 2. That's just equal to x over 2, like that. Okay? So that's how that goes, is that area is x over 2. Does that make any sense? Okay. Now we're going to go on to a triangle and show you something. Okay, so I'm going to erase all this stuff right here, and now let's look at the big triangle. So if we look at the big triangle, okay, what do we have? We have 1/2 base times height. So if you look at this one now, we have to do another thing on this. The base of this triangle is now OC. Okay, like that. OC is the base. The height is now BC, like this. Okay? Now, what we end up having, of course, we have 1/2 base times height like that. Well, the other thing on this is the tangent on this. If you think about the tangent, isn't the tangent like opposite over adjacent? Okay, so opposite this angle X is BC, and then adjacent is OC. So that's why we write that like this. Now I'm going to talk through the last step without going through the details, because again, all I'm trying to get is you guys an idea on this. So what happens is, these are the three things that we have. We have 1/2 cosine x, sine x is less than x over 2, is less than 1/2 the tangent of x. Okay, that just kind of comes from that original inequality I did. And then what they're saying that you can do on here is you could replace this tangent with sine over x, and I'm not going to go through all the details of this, but if you replace that with sine over x, work out a little algebra, ultimately you end up with this part right here. Now, you can just look at the details on this. Now I want to kind of talk about what this means. So if you look at this inequality, if we did the limit as x goes to 0 of cosine of x, that would end up being 1. If you just plugged in 0, isn't the cosine of 0 just 1? Okay. Now if we look at the derivative of this, or I'm sorry, not the derivative, the limit as x goes to 0 of 1 over cosine, okay, if you plug that in, what's the cosine of 0 again? It's 1. So we get 1 over 1, so we get 1. Okay? Remember we talked about this thing called the squeezing theorem. Well, the squeezing theorem comes in handy from time to time when we develop things. So the idea is, if that limit is 1, and if that limit's 1, then doesn't the limit of that also have to be 1? That's what the squeezing theorem said. Okay? Now, you guys don't have to ever reproduce the details of that, but I think it's good if you look at that and see if you can make sense of this. Okay? The higher up you get in math, the more abstract it gets. This is the time when you start beginning to look at this stuff a little bit better. So what does this mean? So it gives us a result that limit of sine x over x is equal to 1. Okay, let's move on. We're going to get to the main stuff that you guys got to know. So I'm going to go ahead and do a couple of limit examples on this, and then ultimately we'll try to finish up by getting the derivatives of these things put together. Okay, now, On this problem, we're going to do this limit graphically, which is easy. You guys won't have any trouble doing that graphically. Analytically, there's a couple little tricks I want to show you. So at the side here, I'm going to write down what we just figured out. Limit as x goes to 0 of sine x over x. We just figured out that that was equal to 1. Okay? That's kind of a fundamental result that we did on the last page then. Okay? Right? And I'll back up on that and just kind of show you what I meant. Is we're going to end up looking at what this limit right here is. Then we'll look at what this limit is in a similar way. And then ultimately we're going to lead up to figuring out what the limit of trig functions are then. Okay? All right. So if we're going to figure this out graphically, just get your graphing calculator out. Let's do it the easy way. This won't be any big deal to you, I don't think. So just put this in your graphing calculator. Put in, erase what you had, and just go sine 4x. Be sure you close parentheses, divide by x. Just do the same window that we've been working on. So get that put in, same window, and let's see what this graph looks like. Okay, that's kind of a neat looking graph. Actually, we probably need to take the window a little differently, and let's make the y go -5 to 5 so we can see this a little bit bigger, a little bit better. So just adjust your y values because you'll see the graph a little bit better if you do. Okay. Now let's just kind of look at what this is. Okay. What does it look visually like the limit of that's going to be as x goes to 0? It's like 4. Okay. That 4x has something to do with that, by the way, too. So yeah, if you went through and did kind of the same analysis, if you picked a number just a little bit to the right of 0, you're getting closer and closer to 4. So it appears, graphically at least on this problem, that that's what you're going to get, okay? So graphically, we're going to get 4. So just draw like a little rough picture on this. So it's like 1, 2, 3, 4. Here's pi. Here's negative pi. So the key thing is it kind of did something like this. Then it kind of wiggled around a couple of times. You can draw the wiggle in a little bit better if you want to. But that's kind of the key stuff that you have, okay? What would happen on that problem as x went to infinity is it would just get closer and closer to each other as you went to infinity like that. Okay? Now what I'm going to do is look at this analytically, and I want you to be able to do a couple of limits like this to look at this and be able to figure this out like this. Okay, so what we're going to do with this one is the idea is we would like somehow to utilize this thing because we now know that thing. Okay, we have figured out and proven that that's equal to each other. So somehow we want that 4x to go away. So one way that you could do this is you could do this. You could basically go through on this. And this is a little trick. We're going to go through and I'm going to have you multiply the top and bottom of that fraction by 4. You know by doing that you're not changing anything, so that's important. So we're going to do sine of 4x times x like that. I haven't changed anything, right? You can do the same, multiply the same thing top and bottom like that if you want to. Okay, you don't change anything. Okay, now we're going to do a substitution. So we're going to just pick a variable like, say something like t. We're going to let t be 4x, and we're going to do a substitution. So we're going to take that t, and we're going to plug it in where we see a 4x. We're going to replace that with t, and we're going to replace that with t. And what we're going to get is the limit as x goes to 0 of 4, now that's going to be sine t over 4t like that. And you might begin to kind of see, not 4t, just t. That whole thing right there is t. So it gives you that. Okay? What I did is I replaced the 4x with t. Okay, does that look okay? You guys see what I'm doing? Yeah, go ahead.
Why did you multiply 4 to the denominator?
Well, I have to do the same to the top and the bottom, and I haven't quite explained why I've done that yet. But if you decide to multiply the top by 4, you have no choice to do the bottom by that. Okay, what are you allowed to do with the 4? We learned a bunch of limit theories. We haven't used them that much, but you can bring it out of the limit. So you could write this as 4 times the limit, okay, of x as x goes to 0 of sine t over t. Now this whole thing right here is going to be 1 because see I changed it into this by just doing a simple substitution. Even though the variables are different, it doesn't matter. We can still think of that as x as t goes to 0. That thing right there is 1, so the answer is 4 times 1, so it's 4. So that's analytically how you do the problem. You have to be kind of clever. Okay, the reason I knew to multiply by 4 over 4 is because I knew ultimately I needed to do that substitution. Okay, and the higher you get in math, the more clever you have to get. Okay, this is a new thing to people usually at this level of class. That's what mathematicians do. They play with stuff. Okay,
So
does that make any sense? Go ahead.
So how to change it in, like so when you change t to 4x, and then you replace it with 4x, how did it just simplify down to 4 sine t over t?
Okay, okay, first of all, this part right here just became t. The whole denominator just became t. The reason I did that too is because we're using the fact that we just proved. I want to change it into that. Because, don't I know that that's 1? That limit's 1? Okay. And see, the thing is, one of the things we learned, if you have a limit of 4 times a function, you can take that constant out. So what happens is the 4 comes out of the limit by a limit theorem, and then this value right here is 1, so 4 times 1 is 4. What you're trying to do is change this expression by being clever into that expression. Okay? See, if I multiply by 4x over 4x, then I have something I can substitute into 4x. Got to be kind of sneaky on that one. Okay? All right, what do you guys think? It's pretty abstract, I agree. Okay, I'm going to do one more like that. And let's see if that'll help you get the hang of it a little better. Okay, so this next one, we're going to do this limit. Okay, and we're going to do this one, I think let me back up to the previous page down at the bottom. Again, just put this one in your calculator. Go ahead and just put this in the calculator. You'll begin to see a little pattern that kind of goes on these limits. So if you put this in, let's see, like this, just erase what you have, and you want to go sine 3x. And you want to divide that by sine of 5x. Just do a graph in the same window, and then we'll kind of see what happens here. And see if we can just numerically figure out what that limit might be. Now, this is a neat one right here, kind of crazy. Okay, that's kind of cool. Okay, got a bunch of asymptotes and stuff in it. That's because there's a lot of places where the denominator is equal to 0. Okay, let's trace it out. Hey, we're doing a limit as x goes to 0, so just type trace. Take a number real close to 0. Okay? What do you think it's going to? Probably 0.6, right? Okay, the closer you get in, the closer you're going to get to 0.6. Okay? So let's just assume that numerically, and you don't need to draw a graph on that, it's too messy and complicated. The thing on this is it looks like graphically speaking, you're going to get about 0.6. So let's just write that down as 0.6. Which is really 6 over 10, and that fraction would reduce down to 3/5. Okay, for our purposes, the only thing that really mattered on this is here was 1 at 0.6. You kind of had a graph in that small neighborhood was looking something like that. That's all that matters. Okay, like that. So it looks like numerically you get 3/5. Now, do you see the 3/5 in the problem? Okay, so like I said, you'll begin to see patterns. Like the last problem, the answer was 4, and you saw that 4x. Okay, so we'll kind of look at, on the next page, analytically how this works out then. Okay? Okay, any question about the graph? Okay? All right, let's do it numerically. Now, we're going to do a very, very similar thing on this now. Okay, we haven't done much with limit theorems, but the only way that you ever understand the real technical part of it is the limit theorem. So we're going to do this like this. We're going to write this as limit x goes to 0 of the top. And we had this limit theorem over the limit as x goes to 0 of the bottom. Okay, that's one of the fundamental limit theorems we learned. Limit of a fraction is just the quotient of the two limits. Now we're going to do this problem right here in a very, very similar way. Remember the only thing we really know is we know the limit as x goes to 0 of sine of x over x is equal to 1. So somehow we got to turn this thing into a sine x over x. So we got to be kind of clever in the way that we do that, okay? So one thing that you could do, and this would be a valid thing to do mathematically, is you could go through and you could basically do something kind of like this. All right, so we would like to kind of maybe get an x down in the bottom there, so we could basically, if we wanted to, at the very beginning of the problem, we could have just done sine of 3x over x all over sine of 5x all over x like that. That's a valid thing to do. We're not changing the problem. If you divide the top and bottom by x, you're not changing anything. You're doing the same mathematical operation to the top and the bottom. So I'm going to go ahead and have you add in an x like that, okay? And that's valid, okay? Now, what we did on this now is what we're going to do in the next step here is we're going to multiply this out like this. We're going to do exactly the same trick that we did on the last problem. So I'm going to do sine 3x over x. I want to just have you rewrite that. Then we're going to do the limit as x goes to 0 of sine 5x over x. And we're going to have to do a substitution, okay? So this is what I do. I'm going to do exactly what I did on the last page. What I'm going to do is multiply this by 3 over 3. Okay, and then I'm going to multiply this by 5 over 5. I am not changing anything. That's a valid algebraic move. You can do the same thing to the top that you do to the bottom, okay? Now, here's the next idea. You're going to do a substitution. That thing can come out. The 5 in the numerator could come out. So what you would have now is you would have this. You would have 3 times the limit as x goes to 0 of sine 3x over 3x. I'm only moving the top one out. I want those 3 x's to be the same, so I can do a substitution. So what do you think I do at the bottom? About the same thing. Bring the 5 out, so you have 5 times the limit of, and see, this is the one that's coming out, so you have sine of 5x over 5x as x goes to 0. Okay, like this. Now you just do a substitution. You could say like t equals 3x, so you can substitute those things with t, and then pick another variable, whatever you want. Let's say u is equal to 5x. Okay, so you get this. So what you would have now is you would have 3 times the limit of sine of t over t, and then that you can just think of that as the limit now of t going to 0, and then 5 times the limit as t goes to 0 of sine t over t. Okay, now here's what you got to see. And you're going to have to study and think about this a little bit. But what is the value of that limit that I'm highlighting right there? That's 1. Good. Same thing with this. That's 1. So what you'd end up getting then, when you put this all together, is this would be 3 times 1 over 5 times 1. So it's 3/5. And by the way, 3/5 is 0.6. Okay, that's what the algebra did. Okay, so that's kind of the mathematical way that you would go about doing that. Okay, and the idea is you're trying to change this. The whole idea is you've got to understand that by making the 3x and 3x match up, then I could turn it into this. That's the idea. Does that make any sense? Kinda? Okay. Kinda at the start's good. It doesn't have to be crystal clear yet, because like anything else, you've got to practice it a little bit.
I'm just still not seeing how the 3x disappears from the top.
Because I did a substitution. Okay, look at this. What I did is 3x got replaced with t. That became t, that became t. Okay, this became u. Actually, that should have been a u and a u is what I should have done. Yeah, so but it's the same idea. See, what I did is I wanted this to be sine 3x over 3x. I wanted this to be sine 5x over 5x, so I could do that substitution. Okay, what you're going to learn anyway, as long as these numbers match up, if that was like a 10x and a 10x, then the limit's still going to be 1. Still works out that way. So that's the idea. Okay? Okay, now, here's what all of this stuff is leading up to, these two fundamental things. And we're going to kind of close off class by doing a proof of one of them. Just one of them, okay? All right? So this is going to be another fundamental thing. You're going to do so much you'll have in your head. The derivative of the sine is the cosine. The derivative of the cosine is negative sine x. So I'm going to prove one of them to finish up class, and then we'll work on this stuff a lot next time. So let's do the proof of this. Ultimately, what you guys get out of this is you feel like, okay, I kind of get the theory. I'm not testing you over it, but I'm just trying to introduce you to the theory part of it, because it gets more advanced as you get higher in math. Okay, I'm wanting you guys to know the derivative rules and how to apply the derivative. So let's do this derivative right here. So the first thing we're going to do is if we do the derivative of the sine of x, we're going to put this in that wonderful limit formula. This is where all this stuff comes from. So what we're going to do is the limit, remember it's f of x plus h, so you're going to do sine of x plus h minus sine of x all over h. We've done that a ton now. Again, that's f of x, which is the sine. This is f of x plus h, f of x plus h like this. Okay, do you guys remember in trigonometry a bunch of identities did you learn? Did you ever learn the sine of the sum of two angles? Please say yes. Okay, that goes like this. Like if you had the sine of a plus b, this is the one that goes like this. Sine A cosine B, same sine cosine A sine B. It was the cosine identity that had the different sign. So that's the one I usually say. Sine, cosine, cosine, sine, same sign. Okay, that's how you remember it. So we're going to apply that now. So we're going to have the limit as h goes to 0, and we're going to replace that with that identity. So it's going to go sine x times cosine h plus cosine x times sine h minus sine x all over h. Okay, that is applying that identity. Now, how do mathematicians figure that out? A lot of times they just play with stuff. Now the next thing I'm going to have you do is we're going to rearrange this a little bit, and we're going to write it like this. We're going to put these two things together right here. So we're going to write this as like this. We're going to group this like sine x cosine h minus sine x like this plus cosine x times sine h all over h. Okay, we can group things however we want to. Okay, now let's pretend like you're the mathematician. What mathematical thing do you see that you can do with that? You can factor a sine out. Factoring comes in very handy a lot of times. The other thing that we learned is we got these limit theorems. The limit theorems keep popping up. So you could technically write this like this. You could write this as limit as h goes to 0 of sine x, factor that out, and you would end up getting cosine h minus 1. And I'm going to break this up into two limits, which I can do that, plus the limit as h goes to 0 of the next part, which is cosine x times sine h like that. Okay? Now again, I don't expect you guys to reproduce this proof, but I like to introduce you to the idea. Okay? So, when we do this limit, this is basically what happens on this. Okay? You may have already forgotten this because it's been a while since we did this, but when we did the limit of cosine h minus 1, that ended up being 0. Okay, if you look back in your notes, when we did that limit, we can do that. So this basically, this sign right here can be treated like a constant. See that x and h are different variables. So technically you can write this as sine x times limit h goes to 0 of cosine h minus 1 over h. And then this part right here, the cosine of x is like a constant because it doesn't match with that h variable. So you can bring that out and multiply that by the limit of h goes to 0 of the sine of h. Okay, sorry I'm running out of room here, but I'm almost done with it. Okay, so here's the idea. This thing right here we did figure out was 0. Okay, so that means that you're going to have sine of x times 0. You bring down the cosine. Now, if you did this, you guys remember what the sine of 0 is. You can just plug the h equals 0 in. The sine of 0 is 0, right? Okay? Well, no, the sine of 0, if you're looking at, hold on, I just must have done something incorrect here. That's okay. Cosine out. Oh, no. This is, what did I do wrong here?
I have a question.
Yeah, go ahead.
A couple steps ago, when you split up the limits, should you have kept an h underneath the cosine x and sine h?
Yeah.
That may have been what messed me up. So let's see, I had this. Oh, I'm missing the h. Thank you. Getting in a hurry here. Okay. All right. So what you end up having then is this part right here. If you look at this part right here, didn't we learn that the limit of sine x over x was 1? Okay. Yeah, so what you end up having is you have this. Now we have 0 plus cosine x, so it's equal cosine x. Now we're done. That's your proof. Sorry about that. Okay? Isn't that cool? Now remember, you guys can go back and look at this stuff because I'm posting them now. So